Alright, hello everybody. Today we're going to be talking about the isomorphism theorems. At the end of last video, we introduced one, which showed that if you have a group homomorphism, then the quotient of the domain group by the kernel of that homomorphism is isomorphic, or sorry, just the homomorphism. Then that quotient is isomorphic to the image of the domain under the homomorphism. So we're going to show, or we're just going to do a bunch of, um, I have three examples to work through. And these are just different scenarios that pop up a lot. There is one thing I want to say that I forgot to mention last time, and that is that normal, or I guess I'll just say normality, is not transitive. What does that mean? It means that if K is a normal subgroup of H, which is a normal subgroup of G, K K may not necessarily be normal in G. Furthermore, if we have the setup that K is a subgroup of H, which is normal in G, then K is normal in H. Okay. So, I just wanted to point this out. It's a little weird at first. You just have to work through the definitions. You can try, as you might, proving that normality is transitive, but it will not work out for you. The smallest example that you can find of sort of a chain of normal subgroups would be in a group of order 8, which is actually a nice coincidence because 8 is the smallest order in which you can have sort of the group and then two subgroups like this, with this one not being trivial. Of course, if this were the trivial subgroup, then it would be normal, but that's besides the point. So I just wanted to point that out. I meant to say it last time. Okay, so let's get into the theorem, the first theorem, and yes, here comes the reason why I wanted to say that spiel. So we're gonna have K normal in H, normal in G. Of course, we don't need to specify this, but I might as well write it. And we need to specify that K is normal in G. Then there is a homomorphism from G mod K to G mod H. Given by, I take the K coset xk and I map it to xh. And this is a surjective homomorphism with kernel equal to H mod K. Okay. So the first thing we have to do, again, is show that G is well defined, right? So we had to do this step last video, and again, this always is going to happen whenever you're defining a function on a coset space, or at least when you define it like this, right? So if xk equals, it's really hard to distinguish capital and lowercase k's, but I'll do my best. Then g of xk is xh by definition, and then g of xkk is xkh. Now, since k is a subgroup of h, we know that little k is in h, and so therefore kh is equal to h. And so this is what we needed. Again, well-defined just means this definition, which relies, we're choosing a representative to define our function, but we need to make sure that that choice is well-defined. If I choose another representative, I have to get the same thing. Okay. Next, we have to show this as a homomorphism, which we do by taking a product inside. This is the same thing as xyk, which is xyh, and then this is xh, yh, and this is g of xk, g of yk. Okay. Next, we show it is surjective. So if xh is in the factor space G mod H, the factor group, I should say, then I mean, really, the thing here is that since x is a representative and I'm choosing it from G, and I'm also choosing representatives from G for G mod K, like I can just take this representative and use it here. So it's kind of like a silly sort of like it's a very, very trivial step. Now the kernel of G consists of x, or I should say xk in G mod K, such that xh equals h, which is the same thing as xk in G mod K with x in h. And so this is by definition h mod k, because all my representatives are coming from h and not from G. And so that proves this theorem. And what this theorem says, we can use the first isomorphism theorem. And so we get that G mod K mod H mod K is isomorphic to G mod H, which mimics normal fraction rules, which is pretty nice. Okay. On to the next theorem. We're going to start with f from G to G prime be a surjective homomorphism, and let H prime be normal in G prime. And we're going to let H be the inverse image of H prime. Then G from G as a function from the group G to G prime mod H prime is a surjective homomorphism with the kernel being H. Okay. Now, G is the composition. Oh, and I should specify how we're defining this. G of x is going to be equal to f of x h prime. Now, G is the composition of f and f prime, which sends G prime to G prime mod H, right? So the canonical homomorphism for G prime, which sends elements x prime to x prime h prime. And so, right, G of x is equal to f prime of f of x, which equals f of x h prime. Since the composition of homomorphisms is homomorphism and composition of surjective, right? So notice f and f prime are both surjective. These are both surjective. So G is a surjective homomorphism. Now, the kernel of G consists of x in G with f of x h prime equaling h prime, and so this is equal to the x in G such that f of x is in h prime, and this is the same thing as the inverse image of h prime, which is h by definition. And so that proves the theorem. And again, this theorem is going to give us an isomorphism theorem, which says that G mod H is isomorphic to G prime mod H prime. Or more generally, G mod f inverse of H prime is isomorphic to f of G mod H prime, where H prime is a normal subgroup of f of G. Okay. And so there's one last one. So we're going to let H be a subgroup of G, N be a normal subgroup of G. Then the product Hn is going to be a subgroup of G. And F from h to hn over n given by f of h equals hn is a surjective homomorphism with kernel being h intersect n. So you can see the format of all these theorems is the same. We have some scenario. We construct a surjective homomorphism with a known kernel, and that allows us to use the first isomorphism theorem to construct an isomorphism of quotient groups. So the first claim is that Hn is a subgroup of G. And so we just go through the works for that. So notice that H1N, H1N1 times H2N2, right? So this is a product of elements in Hn. We have to show that this itself is an element of Hn. Now, since n is normal in G, then we know that H, even though it's picked from H, it's also an element of G, and so we can swap around here, and we're going to get the H, the G element, well, this, imagine this is just an element from G, stays the same, but then N1 can change, right? In generality, it changes, right? But it doesn't really matter. This is of the form H times N, so this is in Hn. So that shows that the product of elements in Hn is in Hn. The inverse of an element in Hn is, right, N1 inverse, H1 inverse. And then we can swap around. We get H1 inverse N2, and this is also in Hn. So again, this swapping around has to do with n being a normal subgroup. And then finally, you have to show that that Hn contains the identity, but of course it contains the identity because H and N both contain the identity. So E equals E is in Hn. So that shows the first claim. Okay. Now, clearly, or I should say, since E is in H, Hn contains N. Thus, since Hn is a subgroup of G which contains N, N is normal in Hn, and that's what allows us to take this quotient group here. Okay. All right, so let's go ahead and show that F is a homomorphism first. So let's say I take a product. This is going to be H1, H2, N. Since this is a normal subgroup, I can just split it like normal, and this becomes just f of H1, f of H2. And so this is F is a homomorphism. If now if I choose Hn to be a coset of Hn over N, right? So notice that this product and then quotient, it really it seems kind of redundant, um, because we're like getting rid of the n, but we kind of need it to deal with. We don't have any specifications of how h and n are related to each other, so we kind of have to take the product here. Then f of h. And so what this is saying is that if I take a coset, I know the representative, and then I have something that will spit out. So f is surjective. Now the kernel of f is the x in h such that hn equals n, which is the x in h such that h is in n, and so this is h intersect n. And that's exactly what we wanted to prove. And so as one final isomorphism theorem, we get that h over h intersect n is isomorphic to hn over n. Okay, and so that concludes the isomorphism theorems. So a lot of these scenarios will come up in the next few videos, and especially later on in things like Galois theory. You have some this scenario especially, I believe, comes up in Galois theory. So these are important to know. But the most important one to know is the first isomorphism theorem. You should know that like by the back of your hand, that I can take a quotient by the kernel of a homomorphism, and that's isomorphic to the image of the homomorphism. Because really that first isomorphism theorem is the key step in all of these. I mean, obviously, all of these theorems that we proved by themselves are just constructing surjective homomorphisms, and that's the setup for us to use the first isomorphism theorem in order to turn a surjective homomorphism into an isomorphism. So anyway, I hope you enjoyed this video, and I'll see you in the next one.